Thank you very much to the organizers for inviting me and their tremendous efforts in ensuring a productive workshop despite all the challenges. And thanks to all of you for tuning in and staying till the end. While it's wonderful to be in Santa Barbara, I'm very much missing in-person interactions with many friends and colleagues who I see are online. While I'm a theorist, the bulk of my talk today will describe very recent experimental results that we posted last month in collaboration with the Google Quantum AI team, reporting the first observation of a discrete time crystal on a superconducting qubit-based quantum processor. While I will focus on time crystals as a specific example, a general theme of my talk will be on the use of near-term noisy quantum computers as experimental platforms for probing non-equilibrium quantum dynamics, and various specific ideas on this are fleshed out in our theory proposal from last year. Okay, so indeed, as has been discussed several times in this conference, breakthrough advances in the development of artificial or designer quantum simulators across a variety of platforms is giving us access to a whole new class of many-body experiments. And while some of these platforms, including Google's, may be broadly motivated by the quest to build a fault-tolerant universal quantum computer, in the near future, we have access to this so-called NISQ regime, which is 100 or so decently good, but still noisy qubits, right? And now many computer sciencey quantum algorithms, for example, factoring large integers, are very sensitive to noise. So we can't actually get very far in such applications with the current systems. However, a quantum computer is also necessarily a highly controllable many-body system with a sizable Hilbert space. So it's natural to ask what kinds of physics they can host and discover when viewed as new experimental platforms for many-body physics in their own right? And I want to reiterate again that I don't want to view these platforms as universal fault-tolerant simulators that can implement any unitary transformation. And so in particular, they could solve for the ground state of some complicated many-body Hamiltonian, such as the Hubbard model of superconductivity. But here we're interested in physics that these platforms can immediately and naturally realize versus physics that they may universally and asymptotically realize, right? So for analog simulators, the natural evolutions are time-dependent Hamiltonians innate to some given platform, for instance, the Bose-Hubbard Hamiltonian in a system of ultra-cold bosons. And for digital simulators, such as Google's platform, the natural evolutions are quantum circuits built out of unitary gates and non-unitary measurements, right? So while these natural evolutions are indeed quite far from the typical regime in which condensed matter physics operates, wherein we search for universal phenomena and interesting quantum order in equilibrium many-body systems at low temperatures, while high temperatures or non-equilibrium regimes are usually non-universal or classical, fortunately, there are problems in many-body physics, particularly in quantum dynamics, that do appear to be very well suited to the quantum hardware and are relatively robust to small amounts of noise, right? So specifically, a parallel set of developments in quantum statistical mechanics has recently shown how we can ascribe a sharp notion of robust and universal phase structure, even to many-body systems out of equilibrium. While doing this in full generality is still largely open, we specifically will have in mind systems that never reach thermal equilibrium by virtue of being periodically driven and many-body localized. And here, a realization was the fact that while equilibrium thermodynamics goes out of the window, phase structure need not. So indeed, one can get new kinds of dynamical non-equilibrium phases in this setting, defined via a concept known as eigenstate order, which I will describe to you later. These phases are completely invisible to equilibrium thermodynamics and may even host forms of order that are forbidden by equilibrium thermodynamics, right? So the time crystal will be a particularly distinctive example of such a non-equilibrium phase with a unique pattern of spatiotemporal order. I should mention here that some of you have no doubt seen a few headline experiments in time crystals from a few years ago, which claim to see signatures of this phase in various different platforms. But closer analysis has revealed that a genuine realization of this phase, or any ordered out of equilibrium phase for that matter, has proved elusive for various challenging reasons in each of the platforms in which it has been explored. So I'll describe what these challenges are and how the versatility of Google's platform allows us to overcome them. Okay, so let's start by heuristically defining a time crystal, right? So a time crystal is, roughly speaking, a macroscopic clock. The rules underlying the system, or the equations of motion, are time translational invariant, but the motion or the state shows spontaneous periodic motion. This is exactly analogous to other forms of broken symmetries, for example, spatial crystals that break spatial translation symmetry. Okay, but this definition, as stated, is too broad and needs some caveats to exclude certain trivial cases. So first, we want to consider conservative systems with no net energy input, right? Indeed, battery-operated clocks are ubiquitous, and these shouldn't be called time crystals. Next, we want to consider genuinely macroscopic many-body systems, right? So a definition of a phase in general requires us to be in the limit of an asymptotic many-body system, or the thermodynamic limit. But this is especially true, and you might think that this is not so important for time crystals because you're working in time, so maybe you only need the limit of infinite times. But actually, few body systems routinely break time translation symmetry and exhibit recurrences and revivals in their dynamics. So even for time crystals, this limit of a macroscopic many-body system is absolutely essential, right? And so in summary, we're looking for macroscopic many-body systems that spontaneously pulse forever of their own accord with no outside field of energy, right? So this by now starts to sound perilously close to a perpetual motion machine, which has been roundly rejected by the laws of thermodynamics for good reason. And indeed, there are various proofs which explicitly forbid the existence of time crystals in equilibrium settings. Okay. So the recent progress on this idea actually arose in a completely different context. My collaborators and I were not thinking about time crystals, but rather about phases of matter in periodically driven flow case systems. Of course, in this context, equilibrium thermodynamics or any of these no-go theorems have nothing to say, right? And while I won't have time to go into much depth here, I'm just going to list the features that will allow us to obtain a time crystal in this setting, right? So the first is that the Hamiltonian by itself has this periodic time dependence. So it's not time translation symmetric in a continuous sense, but only in a discrete sense, in that the system only comes back to itself after integer multiples of the driving period. So to break this discrete time translation symmetry, we require our observables to show a response at a different frequency, rather a subharmonic frequency. So for instance, the observables should show period doubling or period tripling or some multiples of the driving period for it to be a time crystal. Okay, so this is like a charge density wave on a lattice, but this lattice is in time. Now, because this is a periodically driven system, if the system was going to reach thermal equilibrium, in the absence of any conservation laws, the equilibrium state is simply a trivial infinite temperature state. So we need many-body localization to avoid heating to infinite temperature. In order to define a phase of matter, we're going to want this phenomena that we see to be robust over a range of parameters. And finally, what this phase will have is what's known as spatiotemporal eigenstate order, which I'll define for you in a second. But the phase is characterized by long-range order in space and period doubling in time. And what this eigenstate order tells you is that the phase should be robust not only to changing parameters, but also to changing initial states. So you should see this kind of period doubling behavior no matter what state you start from, okay? So that's a quick summary, and we'll go into each of these in a bit more detail. But before doing that, I want to emphasize that period doubled oscillations by themselves are not a new phenomenon in physics. In fact, they go back more than a century to the work of Faraday, right? So they show up in all sorts of contexts, ranging from parametric oscillators to Faraday waves. So we're not looking for just period doubling, okay? But because this kind of phenomena can exist in various settings, but all of these well-known familiar settings are generally dissipative, or they're one or a few or effectively few body systems, okay? So even if it looks like it's a macroscopic system, actually the dynamics is described by only one effective degree of freedom, okay? And instead, we are interested in these genuine many-body phases of matter in isolated, non-dissipative quantum systems, and we want to see these quantum coherent oscillations forever in this setting. And to do so requires Floquet-MBL, and these systems exhibit spatiotemporal eigenstate order, okay? So let me quickly describe what eigenstate order is, which allows us to define time crystals more precisely. This is a new paradigm in quantum statistical mechanics, which gives us a sharp framework for assigning phase structure without relying on ground states or equilibrium Gibbs states or even time-independent Hamiltonians, right? So what happens is that individual many-body eigenstates can display non-trivial order and quantum correlations, even as Gibbs averages over these eigenstates look featureless. Okay, so what we know and are very familiar with, especially in Santa Barbara, is the eigenstate thermalization hypothesis. And in a thermalizing system, what that tells us is that observables evaluated in individual many-body eigenstates agree with the Gibbs averages across eigenstates at the appropriate temperature. However, in many-body localized systems or Floquet unitaries, these don't obey the ETH, right? And so highly excited eigenstates have area law entanglement and in many ways resemble gap states, gap ground states, right? So what happens is that this gives us a way to get order across the entire many-body spectrum, including in highly excited states that would nominally be at infinite temperature. Okay, so the interesting quantum order that usually lives only at low temperatures exists across the entire spectrum in individual many-body eigenstates, even if averages over these eigenstates look trivial. Okay, so this allows us to evade various no-go theorems from equilibrium thermodynamics, including Landau-Peierls or Oshikawa-Watanabe's theorem in the case of time crystals. And importantly, even though we're using eigenstates to very sharply define and precisely define what this phase of matter is, the eigenstates by themselves are not measurable, but this eigenstate order has measurable signatures in dynamics from simple experimentally preparable initial state. Okay, so let me very quickly say what this means in a Floquet system. It's a very natural generalization, right? So in a time-independent Hamiltonian, if your system is thermalizing, typically the low energy states or the ground states are ordered, whereas most highly excited states don't show any order. In a Floquet system, if your system is thermalizing, it heats up to infinite temperature in the absence of any other conservation laws. So all states look thermal or infinite temperature or boring and unordered if you're thermalizing. But if you're many-body localized, then every single Floquet eigenstate across the entire spectrum can show you long-range order. Okay, now in the Floquet system, I've drawn my eigenspectrum as living on a circle. That's because the eigenspectrum that I'm referring to are the eigenvalues and eigenvectors of the Floquet unitary, which is the time evolution operator over one period. And because of the periodicity in time, these eigenvalues define quasi-energies that live on this unit circle, right? So it's just like quasi-momentum live in a Brillouin zone, quasi-energies live in this unit circle. Good. So that's what I mean. A Floquet spectrum has order across this entire across the entire spectrum. And just to be concrete before I get into the experiment, let me just take a minute to describe an explicit model so you have a sense of the types of systems we're talking about, right? And the simplest model is a time-dependent Ising Hamiltonian. So for instance, the drive is one single Floquet period is defined by time-dependent Hamiltonian, which for the first part of the period looks like Ising ZZ interactions, and for the next part looks like a transverse field, okay, which implements rotations about the z-axis. And then this period is repeated in time. This model is mappable to free fermions. It's exactly solvable. It has this Ising symmetry, which corresponds to flipping all spins. You get 4 phases, and one of these phases, the pi spin glass, happens to be the time crystal phase. To understand the properties of this phase, let's park ourselves at a value where the x part of the drive is implementing an exact pi rotation, right? So there, if you start with some pattern of spins, they get exactly flipped in time and then flip back. So, trivially, you get this period doubling. And importantly, this is the part about spatiotemporal order. If you look at the eigenstates of the Floquet unitary, each eigenstate looks like a long-range ordered cat state. Okay, so instead of the up plus down and up minus down cats in a ferromagnet, every single eigenstate is now a random cat state with long-range order and non-zero correlations, long-range correlations. But these cats are paired in quasi-energy. They're not degenerate. They're paired at frequency omega over 2 or pi at pi. That's what this pi refers to. And what that means is that if you measure these unequal space-time correlation functions in many-body eigenstates or any state, and look in the limit of large distances and long times, you get something non-zero. Okay, so this is how you can precisely define what the spatiotemporal order in a time crystal is. And the reason this is all interesting is that this behavior is not limited to one particular value in parameter space, but is actually robust. So you can add, you can do rotations at angles other than pi, so imperfect rotations. You can add all sorts of other interactions, Ising symmetry breaking terms, all of that, and this response is expected to persist. Okay, So that's the theory end of it. So what's actually involved in seeing this phase experimentally, right? There are various challenges, and a lot of pioneering experiments pave the way for us to understand what these challenges are and to see how to overcome them, right? Okay, so the first challenge is that we need to actually realize the phase, okay? So we actually need the interactions and the types of disorder and the range of interactions, the types of interactions that allow your system to have many body localization, okay? And we need to be able to vary the drive parameters, vary disorder realizations to get this kind of stable phase, okay? So that's a question of quantum control and programmability. What are the types of interactions you can actually realize? And actually, this is much harder than it sounds. All of these early experiments on time crystals on closer inspection actually did not have and cannot have, or is very challenging for them to have, the types of disorder and interactions that can give you this MBL time crystal. Okay, so all the prior experiments already failed at this stage. But even if you work with a platform where numerically or analytically, you can realize the types of interactions that can give you this phase in theory. In practice, you're working with a NISQ system, which has various limitations. It has a finite coherence time, it has a finite system size. So you want to probe an asymptotic non-equilibrium phase, which actually exists, truly in the limits of infinite times and infinite sizes. But you want to be able to probe this within these realistic experimental conditions. Okay, so after you realize the phase, to actually be able to experimentally establish its existence and stability and to distinguish it from various other kinds of transient phenomena requires various other checks that you have to perform, right? So for instance, to mitigate this effect of finite coherence time, we need to distinguish the decay that could be induced by unwanted external decoherence from intrinsic instability of the phase due to quantum thermalization, right? So if you see some signal that's decaying in time, how do you know whether that decay is coming from something intrinsic so that your system is not actually realizing the phase, even if it was perfectly ideal, or if it's just caused by external decoherence that will get more and more mitigated as your noise improves, right? So that's the first challenge. The second is, I mentioned this thing about eigenstate order, and this is really fundamental. Like that's what defines the sharp non-equilibrium phase. So how do you actually probe this entire many-body spectrum? Okay, usually it's easy for experimentalists to prepare one or a few special states, but those can show you long-lived oscillations for reasons that may have nothing to do with eigenstate order and many-body localization or the physics of a time crystal. So you have to probe this entire spectrum in some kind of efficient way to distinguish eigenstate order from various transient phenomena that may be exhibited by special initial states. And finally, you know that your platform is only going to have a finite number of qubits, whereas a phase of matter is sharply only defined in this infinite size limit. So we need to be able to demonstrate the stability of the system through increasing system size. So what's really interesting is that while NISQ platforms have these various limitations that get in the way of, theoretically establishing the existence and stability of the phase, they also have a great degree of versatility and flexibility to mitigate these different limitations. Okay, so we'll show how these NISQ systems actually have some built-in mechanisms for overcoming each of these challenges that are intrinsic to them. Good. So the first challenge is just getting the parameters right and having the requisite amount of control to realize the phase. So for this, there's a native gate set that exists on Google's Sycamore device. This has these types of Ising interactions that we needed. It also has other XX and YY interactions, but as we said, this phase is stable. So in our theory paper, we mapped out a phase diagram for this model, which is again doing this type of drive where you have dominantly Ising interactions. That's from the ZZ piece, plus all sorts of other stuff. The theta is this XX plus YY. The G is the rotation about the x-axis. And as a function of G and theta, you can map out a phase diagram. Near theta of pi, you have a time crystal. In the opposite limit, you have a paramagnet. And in the middle, you have this broad thermal phase. Okay, this is a picture of the chip. It's actually a 2D chip. with these qubits, but you can isolate a 1D system from it by just by turning off certain couplings and turning them off. In the actual experiment, we actually the theta parameter was set very close to 0. So we basically just work with these almost Ising interactions, longitudinal fields, or not almost Ising, strongly Ising interactions, longitudinal fields. We had disorder in the Ising couplings, and then we had this transverse field for the rotation. And then the experiment was performed in a linear chain of 20 qubits. Okay, so that's the setup. You can feed in any initial state that you want. We worked with different Z states that are represented as these bit strings. These X's are the rotation angles. These are the ZZ gates. These are the random Z fields, and then you can go in and measure things. Okay, so great. What do the signatures of this phase look like? The simplest thing you can measure, which is indeed what all the experiments in the past have measured, is a spin-spin autocorrelation function. Okay, so if you just measure the spin-spin autocorrelation function starting from different states, in the time crystal, you expect this period double signature. So for instance, if you started with the all up state, after one period, you're all down, then you're back to all up and so on. Okay, so if you measure the autocorrelator of a single spin, it oscillates in this way. In a thermal phase, this autocorrelator quickly relaxes to 0 because it's infinite temperature. And in the paramagnet, because it's many body localized, it retains some memory of its initial condition, so it saturates to some non-zero value. Good. So, we looked at this autocorrelator over different disorder instances, over different drive parameters. So here is what the experimental data looks like at a parameter value deep in the thermal phase. And indeed, you see that your correlation functions quickly decay to 0. Here it is for a different parameter deep in the MBL phase. And you do see period doubled oscillations. Okay, so you see a sharp contrast in the behavior at these two different parameter values, which lasts about 100 Floquet cycles. Okay, which is roughly the coherence time of the experiment. However, we see that this period double signal is also mitigated, is also modulated by this exponentially decaying envelope. Okay, so this raises a question, which is, given this exponential envelope, how much of this decay is coming from some internal thermalization mechanisms that may be causing the system to relax even in an ideal setting, versus how much is coming from external decoherence, right? So to address this question, we used one of the great or a feature that comes from the flexibility of these platforms, which is we were able to do like an echo or a time reversal circuit. Okay, so we did a forward time evolution for some number of periods, and then a backward time evolution, okay, for the same number of periods. And then we got a signal that comes from the composite of these two circuits, okay? So if you were an ideal decoherence-free system, this would just implement the identity and you should see nothing. So any decay in these black lines, which are the echo circuits, are coming purely from the external decoherence, okay? So the quantum thermalization would cancel out between these processes, but the decoherence would add up, okay? So in this data, this is the pink signal and the blue signal are for the actual circuit, whereas the black lines are for this kind of echo circuit, which in an ideal setting would just be 1, okay? So then by dividing the actual signal from the signal which probes the effect of decoherence, we can separate out in a rough way the effect of the decoherence from the internal dynamics. And what we find is indeed this clear contrast where in the thermal phase, you see the signal that decays to 0 very quickly, whereas in the MBL phase, you see this period double signal with no hints of decay up to this long times. Okay, so that was the second challenge of addressing these finite coherence times. The third challenge is probing the entire spectrum, okay? In an eigenstate, and this is really important, this is really one of the key ways in which we can distinguish what we did from what a lot of the other experiments did, right? So in an eigenstate order time crystal, all states in the spectrum have long range order and period doubling. So the initial state really should not matter. And indeed for this experiment, this is just data for 3 different states. And you see that the signal basically looks the same for all of them, okay, once you disorder average. Whereas in various other pre-thermal or DTC-like phenomena, some states can have long-lived period doubled oscillations, whereas other states thermalize more rapidly. Okay, so we probe such a model by changing the parameters in a way, and here you do see a difference between these different initial states. Okay, to look at this more systematically, we prepared 500 different initial states for each of these drives. These nil and polarized states end up being special states with respect to an effective Hamiltonian that can approximately govern the dynamics for this particular pre-thermal special control case that we picked. And indeed, what we find is that these states are clear outliers with much higher oscillation amplitude, whereas other states have much lower amplitude. On the other hand, in the actual MBL time crystal, there is no systematic state-to-state dependence in the oscillation amplitude. Okay, all states behave the same, rather than some special states. Okay, so this is a key feature for probing this eigenstate order. Okay, but I should say here that we want this protocol to be scalable. Okay, sampling 500 states is already a lot of work, but this is still a tiny fraction of the spectrum for 20 qubits. Okay, so as you scale up the system, it really isn't practical to say that, okay, we're going to sample 1,000 states or 2,000 states. So we want a more scalable alternative to probe the entire spectrum. And again, here, the great kind of flexibility of the NISQ platform gives us a solution, this time from quantum typicality. Okay, so what quantum typicality allows us to do is prepare a random, highly entangled many-body state. We can do this by just starting with a simple unentangled state and running it through a random quantum circuit, okay, which in general, with sufficient depth will just give you a highly entangled random state. And then if you measure your autocorrelation function in this random state, this gives you an accurate spectrum average from a single state up to exponential accuracy. Okay, so you can probe the entire spectrum in one shot. And again, once we do this, we see these stable oscillations in the time crystal, but not in the thermal phase. Okay, so this is key to diagnosing the eigenstate order. And finally, the last challenge is finite size analysis. And again, here we can vary the length of the system by varying the number of qubits that are included in our SNEAK. And we probe this spin glass order parameter, which measures the persistence of not just the temporal order, but spatial order in the initial state. And this is supposed to increase with L in the time crystal, decrease with L in the thermalizing phase, and it shows this nice crossing. Okay, so this is an actual finite size analysis of a phase transition that can be performed on this NISQ device. Okay, so this is my last slide. And what, here I just want to connect to a slightly broader theme, which is that of verification of quantum dynamics. Okay, so in any kind of phase that we may want to study, the signatures of this phase will generally be quite simple, okay, for them to be understandable by humans, right? Like for a time crystal, something should oscillate, right? But if the signatures are so simple, it's also easy for someone to spoof those signatures or for us to be able to get those signatures in different ways. So for instance, all these different first generation experiments in time crystals and NV centers, trapped ions, NMR crystals, they all probe this kind of magnetization dynamics from one or two special initial states, and they all got signals that actually look very similar to this Google signal. Okay, so if this is all you had, you would have no, you don't know which of these is actually realizing a time crystal and which isn't, even though closer theoretical analysis reveals significant or fundamental obstructions to realizing time crystals in each of these different platforms. Okay, so the scalable protocols and the different checks that we employed in this most recent experiment can be viewed as first steps towards a broader goal of kind of efficiently verifying quantum dynamics. If your quantum computer says that it achieved a certain phase of matter, how do you verify that, right? Like just like if your quantum computer said it factored two integers, is there an efficient way of verifying that? In that case, it is. You just multiply the two factors. But in the case of dynamics, it requires more effort, and some of these protocols and checks that we employed can be useful in that broader program. Okay, so as a summary, this is an application of a NISQ device to achieve this first demonstration of this non-equilibrium phase of matter, the time crystal. This experiment addressed various challenges and furnished various scalable protocols that may be useful for future experiments. And this also points to a broader set of interesting many-body problems with random circuits that could be studied on these platforms in the future. And this is my most important slide. I want to thank my collaborators and especially call out Matteo Ippoliti, who's a postdoc at Stanford, who led all the theory work on this project, and Xiaomi and Pedram at Google, who led the experiments, and of course the entire Google team, of which there are too many people to name. Thanks.
So thank you very much for this very nice talk. We are open for questions. Okay, so in the meantime, I'm going to ask. So the results you showed correspond to 20 qubits, right?
Right.
And which are the maximum size that could be achieved so far?
Right. So in principle, so we had to use a particular gate set that was only developed a few months ago to get disorder in these Ising couplings. And that was calibrated and so on a smaller chip with 20 qubits. But there's no fundamental reason that we can't scale up. And in fact, the Google team is actively working on scaling up or implementing the gates even on their bigger chip. So in the very near term, this could be done on 50 to 100 qubits. 20 is not fundamental in any way.
And the protocol is always the Floquet field in the transverse field introduced, right?
That's right. That's right. And the protocol, these other protocols for the time reversal and this kind of quantum typicality, that was one of the reasons why we really wanted these scalable protocols, so that even when you go from 20 to 100 qubits, nothing about the scalability of these protocols breaks. So you can do exactly what we did on 100 qubits as well, and get at the answer. Yeah.
Okay, thank you. So no further questions?
Can I ask a
sure.
question?
Yes, please.
So in either of the MBL phases, either period singling or period doubling,
right?
What's the physics there? Like why does it sync up with the driving frequency?
Well, so in the period singling case, it's the analog of equilibration and synchronization in a Floquet system, right? Because if you have a Floquet spectrum or Floquet eigenstates, then at late times you relax to the diagonal ensemble of those eigenstates, unless there's some special pairing. So that means that synchronization is the default option. So that's the singling. The doubling comes from the fact that you have this pi pairing. So you have this kind of commensurate pairing, and you actually have these two cat states, the plus cat and the minus cat. And you go from, if you start with a product state, it's a superposition of these two cats separated by by pi. So if you expand that out in the eigenbasis, you'll end up seeing this period doubling, because the quasi-energy pairing is commensurate with the driving period.
But wait, so early in the talk, you had sort of in the earlier experiments given stated that I thought stated that the presence of dissipation was like a mark against those experiments in a way. Like
I would say it wasn't so much. I mean, all these experiments have dissipation. They didn't characterize the dissipation, but that's not what's fundamentally different. I mean, it's the fact that they don't have MBL. So actually, if you look at what all these prior experiments did, if you look at the nitrogen vacancy center experiment, it's an experiment with dipolar interactions in 3D. That's too long range to get MBL. So there you just get you get a very slow thermalization. So they see this decaying envelope, but they don't know, is that coming from internal thermalization or external thermalization. And theory work has actually shown that in this case, it's slowly thermalizing intrinsically. In Monroe's experiment, the particular type of disorder they had is not sufficient for MBL. If they had probed more than the polarized state, they only probed the polarized state, which is this blue state. If they had probed other states, they would have seen rapid decay of oscillations and would have realized that they're not a time crystal. even within the dissipation and all of that stuff. And then in this ordered NMR crystal, that was yet another experiment. This is just a 3D ordered crystal. There's no disorder, there's no MBL. And they were probing a very special kind of collective observable. And so they probed a different kind of pre-thermalization. So we actually came up with a checklist for, what you need to stabilize MBL to detect your phase and, and distinguish it from different pre-thermal mechanisms. And all of these prior platforms lacked one or more of those.
So if you, my naive picture for like a dissipation-free system would be like if I take an oscillator that has a natural frequency omega naught, sure, and I drive it at some other frequency omega.
Right.
Then, I will get oscillations at both frequencies. So the response won't be periodic.
Right, but then you're in a single oscillator. So you don't even need to do anything fancy. I mean, this is why I said that you need a many-body system to define a time crystal. Because think of a single spin in a magnetic field, right? It's going to show you Rabi oscillations, but you don't want to call that a time crystal. Right?
Sure.
So if you have many coupled oscillators with some natural frequency that are driven at some other frequency, classical oscillators, to get stable period doubling in that setting actually requires you to have dissipation. I don't know of an example where you can get it without that.
But then wouldn't MBL be like be working against period doubling or period synchronization?
So there's classical settings in the past which have been studied where either for one or a few body systems or dissipative systems, you can get this kind of period doubling, right? But if you have an isolated quantum system, there's no way that I know of, except with Floquet MBL and eigenstate order to really get this asymptotic phase. And there's the MBL. If you have an isolated periodically driven quantum system, that's just going to heat up to infinite temperature. And there you need MBL to kind of prevent that from happening.
Okay. Yeah, I'd like to talk about it more, but I think we can do that offline. Thank you.
So Anatoly, please.
Okay, I'm in the same area, so I just I just want to ask maybe a related question. So I understand like absence of dissipation, it's a separate thing, but the other thing I was thinking, isn't it still synchronization? Because let me take Swiss clock and suppose like every year I synchronize it with NIST or first. Then of course I will synchronize everything in between. So I'll get really perfect order, not just in my whatever original period, but in every period. It's a big number of seconds in a year. So, so in this sense, I would say you said period singling is like just synchronization, and period doubling, I would say it's also synchronization, but plus you have this extra thing.
Well, it's not synchronization. I mean, it's synchronization if you look every 2 periods, but it's nothing.
No, but even in between, what I'm just saying, if you synchronize, I mean, period doubling like happens in nature, right? You have down control.
No, right. So look, so that's why, I mean, again, that's why I wanted, the title of my talk has eigenstate order. I don't, I want to view this whole program as ways of getting non-equilibrium eigenstate order across the entire spectrum in many body quantum systems.
Okay. So
I mean, okay, we can go back to Faraday. I mean, period doubling is not special. I'm giving you that. There's a whole chapter in our review devoted to all the ways in which you can get period doubling.
And if you have physically, if you suppress dissipation,
right,
is of course challenging. The fact that you are synchronized every 2 periods is not actually surprising, because
in a many body system it is. If you have a genuinely many body non-dissipative system, I don't know of any other way to get this. In a one body system, absolutely fine, you can get it. In a many body non-dissipative system that's isolated, I don't know of any other stable way to get it. You can get all sorts of pre-thermal things that may last a long time, but if it's a genuinely closed system and it's genuinely many body, not one mode, not one differential equation describing one mode, I don't know of any other way to do this then.
I'm good, thank you.
Okay, I don't see any other questions. So let's thank the DISTA again. Thank you very much. And I think we should also thank all the speakers of this last session and of all the conference. Also, I would like to thank the organizers of this conference. And I invite all of you to continue in our activity. We continue with the talks tomorrow and the forthcoming weeks. Thank you so much and see you. Bye-bye.